Alright, another draft physics presentation. I think we'll try to do this as some kind of questions and answers videos, so some sort of appropriate title, and I guess I'll number them or something. Try to indicate what the subjects are, if there are specific subjects in the questions. So this is going to be mostly, I think, mass and charge. So I guess those will be keywords. And we'll leave it at that. So James asks, what is mass? And some asshole, which there's such an abundance of, Mickey Farley, your mom. I hate people. So anyway, the mass question is sort of simple, but with a lot of qualifications, right? You could just argue that everything that is has mass. So mass is a quantity of something that everything that's not a nothing has to have. To be something, you're stuck with having some kind of mass, whether you, whether you like it or not. So a photon has some kind of mass. Every bit of force has some kind of mass because it can make something happen. So you just say that mass is just related to being a something. It's just something you have. And the question really is just how does the mass manifest itself in the game. So I would sort of argue that you can see a magnet can have more mass. If I have a magnet and then I have it in gravity, I can make it seem like it has more gravity because the magnet will pull it down and gravity will pull it down. Now it's all the same force, but it's the same force being manipulated around the thing that makes it seem like it's heavier or lighter or more movable. But it's it always has to do with some. There's always pressure, mass that you're surrounded by. It depends on how much mass you're surrounded by, how you appear to move or appear to your mass seems relevant to the other things having mass. But really it's just you only have your mass. But clearly the environment can make it seem like you have more mass because it's doing mass equations. Anyway, probably a more complicated answer than is necessary, but we'll get to that a little further when we get to charge. Alright, and then some other asshole left some comment. To be honest, I thought about this for a while and I'm still skeptical about your theory. Blah, 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 blah. A little bullshit. Post the link to it. Just a complete waste of time joke video. I'm just so sick of you people. So this guy I will block just because. Fuck this. I'm not here doing humor. It's really just not the point. And so, fuck you. Waste my time is really obnoxious. Waste anybody's time is obnoxious. Alright, some other idiot says, photons do not exist. An absolutely useless statement. Now, if you had some prestige in the world of some kind and you were proven to be right so many times about all the things you say, then maybe that could mean something. But in this context, it can't possibly mean anything. It's just a silly bit of drivel that fell out of your mouth. A waste of my reading time. You have to make an argument. You can't just declare a truth. That's what Ken Wheeler does. You have to make arguments explaining how you're right. You can't just say you're right. Shit. Alright. So another comment by Jerka or whatever. Bunch of preamble crap about my other channel. Nothing to do with this. Okay, so he says, on to physics. I agree with some of your criticisms of mainstream physics. Oh, okay. Although I find Bill Grady videos more entertaining. Who cares? Again, I'm not here to be entertaining. I'm just not interested in this. These qualifiers that have nothing to do with the fucking subject. Especially as Einstein Idiot Series videos. Well, so you're just basically telling me you're retard signaling. You understand what retard signaling? You're retard signaling. When you say especially Einstein Idiot Series, where people make fun of people's hair, the German meaning of their name, they spin them around in circles, I mean, you know, you're just fucking screaming to me, don't even read any more of this asshole's comments because he's such a fucking asshole. Amazing. So he thinks this is something I should take note of, that he's more entertained by spinning Einstein images. Then what are you doing here? You think you're going to convince me to do that? To take Einstein's image and spin it around, and therefore I've made an argument? You think you're going to get me to do that? With this whine? With this bullshit? People are just remarkably stupid. Not all his criticisms are valid. Oh, duh. And he gets needlessly rude sometimes. Well, great. So now you're pointing out why the thing you're saying is you are entertained by is moron food, and yet you're I mean, you know, you're not only an idiot, you're a moron. Is that what you're trying to tell me now? You're fucktard signaling, retard signaling, and moron signaling. But he makes some good points, except for the ones that don't exist, like all of them. However, his rope theory is less than convincing, to put it mildly. So the whole video content is absolutely useless. He does a childish critique of conventional physics, and then does an insipid counter theory of whatever, tangled ropes. But it doesn't mean I'm a Tesla nut or electric universe groupie. I don't know where you got the impression that I said that everybody who finds Bill Gates entertaining but stupid is somehow a Tesla nut. Where did I make that argument? But I wouldn't be surprised. I just haven't found a good theory that convinces me. Fine. And the mainstream, with all its warts and fudge factors, is probably the best option from a sorry mix of choices. And it's the best option. Why? So you concede it has fudge factors and warts. I would argue it has completely fantasy characters. It has preposterous perversions of the historical record and the truth. But whatever. Alright, so here he goes. As for your theory, here's a few questions. These are kind of questions I've certainly answered in previous videos, but whatever. What is the mass and electric charge of each ton? So some of this I'll draw eventually. I guess I'll read through them first and then get more specific. 1. So I would argue that the little bits, okay, you keep saying tons now, I call them bits now. Okay, because people can't deal with the word ton, so we're going to go with bit. Alright, there's a bit of force, and then there's bits of matter. Now, the bits of force all have the same property. Every single one of them has the same property. It moves the speed of light and has a mass, a capacity to do that's exactly the same. And we could call it 1. It's the smallest thing we could find or detect. It's always a 1. It's never a half. It's never a quarter. It's always a 1. A 1, a 1, a 1. And the charge is dependent on whether it's a black bit or a red bit, a square bit or a round bit, a up bit, a down bit, however you want to distinguish them. 2 different kinds. Electron reflective, proton reflective. 2 kinds of bits. That's it. So their charge is their color. Their association to matter bits. How they affect matter bits. Okay. How many tons in an electron? A proton. Well, measuring is a little difficult because you have to be able to somehow isolate them in such a pure environment that you can hit them with a couple of little tiny bits of force and see how far they move. But you can surmise there's some lag in their movement. They don't move instantly. So if they had a 1 mass and a force hit them, the force would cause 1 movement, the exact amount of movement this thing had. And clearly there seems to be a lag, so that you have to use more force to push them. They're not equal to a 1, they're a 5 or a 10 or a 1,000. But what exactly they are again, it's really hard to measure because it's really hard to put them in an environment where you can test them with instruments and see them and yet not interfere with them, not create an artificial mass or an artificial movement. It's pretty impossible, actually, to put an electron anywhere on planet Earth and have it in some kind of neutral charge field. Anyway, so how many tons an electron proton? What mechanism guarantees that count? So again, I don't know what that means, but if you're asking me what test guarantees it, none. That's why they have to keep that's why they keep changing the weight of protons. It's because it's really hard to measure. So I don't know. I don't have those answers. I would speculate that because of what we see happening in induction, in electricity, for example, electrons don't stop immediately. A little lag, a little bit of a startup time, a little bit of a slowdown time. So they're not perfectly, they don't move as precisely as the force can move. So that's the only argument I would make for the fact that they have to have some greater mass than the force bits. Alright, how do you account for the electron-proton having the same magnitude charge but mass ratio of 1 to 1836? So the argument is that the electron is 1,836 times lighter than the proton, kind of argument. That the proton is this massive thing. And I would argue that I really shouldn't have to be glued to those numbers because I don't have any reason to think they're accurate. Okay, because I don't think we can measure these things, because the two are affected by different forces. So conclusions drawn are going to be messy. So I guess my answer would be I think that's part of physics where they've overstepped their capacity, overstepped the capacity of their technology to give them an accurate answer. So although they do have the same charge, and it clearly seems to be a difference between electrons and protons in that protons do seem to, they're nucleus type, and electrons are surface type. So protons are interior, electrons are exterior. Seems so. Seeing that model seems reasonable, and that might be an indication that the protons are much bigger than the electrons. The charge density is another question, because that really just has to do with size. One could be more dense than the other. But volume is another question, because volume has to do with how you can capture or interact in the world. Your volume size will dictate how easy it is, how big a target is will decide how easy it is to hit it with bullets. So it's another question that I just don't think they have the technology to answer. Why does the electron explode? Why does the electron explode? Oh, I don't think it does that. With so many tons of the same charge crammed together. Why does the electron explode with so many tons of the same charge crammed together? Why does the electron explode with so many tons of the same charge crammed together? I've already described how, see again, I just sort of insulting because I've been over this stuff so many times in these videos. I mean, one of the start here, you know, video 2 goes through the whole explanation of the charge. And what I'm arguing is that there's a bunch of photons. They're not in the form of photons, they're just the little bits moving back and forth between two electrons. So if this was two electrons, there's bits bouncing back and forth, reflecting. This is black, the little bits are black, the little bits reflect off the black things. They're bouncing back and forth. That, okay, is the energy of the electron. And if the electron moves, that energy releases. That's what you're, that's the force, okay, of the electron. The force isn't in the electron itself. So it's like if I move an electron from one place to another, I move it with voltage. And voltage is those little bits. That's the pressure. So it's the little amounts, the little ping pong balls you could see. Say the matter bits are tennis balls, and you think of the force bits as ping pong balls. It's that kind of thing. So there's a bunch of ping pong balls bouncing, and if I increase the voltage, that means I'm increasing the rate that they're hitting. So I'm increasing the pressure. And if I create enough pressure, the electron loses its bond to a proton, and it goes with the force. The ping pong balls keep hitting it, though. It doesn't move on its own. It moves because it keeps getting hit by ping pong balls. So that's what I'll attempt to draw, explaining the connection between mass and charge. Alright. What makes some type of tons, bits, force bits? Okay, let's just, can you do it? Can you play along? Force bit, matter bit. Electron, proton, matter bits. Force bits are any kind of radiation moving the speed of light. Okay, what makes same type tons repel? The rules of physics, the laws of physics. It's like asking me what makes them go the speed of light. I don't know. It's just one of the simple rules. As I stated, I'm giving you a universe that only has like 4 rules. But they're rules. I can't if I could explain them, I wouldn't call them rules. I'd call them byproducts of rules. Some other rule. I have to call them rules because, yeah, I can't explain why that's the way it is, but that's just the way it is. Black things bounce off of black, red things bounce off of red. And they come out perpendicular when they're opposite colors. Rule. That's it. Just a rule. Alright. Are you just transferring the problem of repulsion down one level without explaining it? I'm sorry. I mean, there's not another physics theory out there. Give me one physics theory. Show me one that explains magnetism and explains gravity with any real force, for any real actor. Go ahead, show it to me. So, I mean, no offense, but what do you want from me? I mean, how am I just transferring the problem? I've given you the simplest rule possible. The black ping pong ball bounces off the black stuff, and the red ping pong balls bounce off red stuff. And you want me to somehow I'm evading some sort of giving you an answer? When, yeah, I don't know why they go the speed of light either. I don't know. I don't know why they exist instead of not exist. You think I'm going to answer those questions? You think any physicist is ever going to answer those questions? If that's what you're waiting for to decide, if that's it, oh well, I can't accept one of these theories as being more logical or rational until one of them explains why the universe exists, then you're going to be waiting a long, long fucking time. Alright. I mean, it's just amazing. I mean, I'm giving you an explanation for repulsion. I'm explaining to you why that's all there really is. There's just repulsion. There's just a push force in the universe. And the only way two things are attracted is because the ping pong balls leave. The ping pong balls bouncing between the two things go out perpendicularly, and then there's no ping pong balls in here, but there's still ping pong balls out here, and that's attraction. That's not good enough for you? When it's 999.99999% more than conventional physics has given you as an explanation, they give you absolutely nothing. And so if I said, well, space is just bent. It's the way it is. It's just one of the rules. It's bent. Do you rag to go on Professor Sloan's videos and rag on him about how he hasn't explained how space is bent, how time is bent? Why are you wasting my time doing that? Why don't you do it to the establishment? Show me where you've done it to the establishment. Show me where you waste their time. Anyway, and again, explain to me how their non-explanation seems so much better than my non-explanation, because they give me so much more details about how magnetism works. I mean, it's just incredible, all the details they give you. The virtual photons do something or other, and blah 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 blah, and electricity happens. That's their explanation. For fuck's sake. I didn't realize how dumb these were. Anyway. Okay. When the tons, the force bits, bounce off each other, doesn't happen. Force bits only hit the matter bits. Force bits only hit electrons and protons. Okay? And matter interacts with force bits, but there's no force on force or matter on matter. Those things don't happen. Okay. How do they instantly accelerate to the speed of force? Well, they don't. There's two things going the speed of light. They hit. Two things leave going the speed of light. Nothing new happens. And I've never said that a force bit hits a matter bit and the matter bit goes the speed of light. Obviously, I've argued consistently and over again that you'll never make a matter bit move the speed of light. I'll take that back. If you put enough force behind an electron, enough voltage, okay, you can push it any speed, up to the speed of the force itself to some extent. I mean, I don't think you could ever reach the speed of light, but you can definitely get closer, as long as you shove enough voltage. But it's a huge amount of voltage. And in the context of the electron and its material volume, the voltage you've put behind it is essentially the force. The electron's almost going to be irrelevant. It's just a conduit through which you can make something happen somewhere else. So if I just pump force into a piece of matter, like in an accelerator, if I just accelerated the force, that is, I just made a bunch of force going around and around, and I smash the force in, the voltage, it won't do anything much. It'll just go into it, it'll spread through it, and scatter out of it. But if I force the interaction between two matter bits that have force between them, that's when you create the repulsion force between them, and that's when you disintegrate them. So you'll explode the material things. If you can shove a material thing into another material thing, the force that's trapped between them will bounce and cause both of them to disintegrate. You can shove force into matter, complex matter, because it will spread. But you can't shove matter into matter, because the forces around the individual little bits won't allow that to happen, and you'll get rebound action. Alright, I think that covers that. Oh, I'm just dead tired. I don't know why. So let's see. Alright, so I'll try to draw some of this and then we'll call it a day. Well, call it a shitty video. Sorry about the banging by the microphone, my mistake. Alright, so the simple rule is, I've sort of been over this before though. So the mass thing, so let me just do a real quick diagram of, let's say, the magnet and gravity. So if I have a magnet and then I have another magnet, oops, I should have done it the other way around to create attraction. Alright. Now there's going to be two forces. So say this is on Earth. So there's two forces involved. Alright, let's put this magnet on the surface of the Earth, just not to confuse things any further. Alright, so there's gravity pushing down. And so this is going to be moved in one part. This is the total force coming down. We know that this is blocking a certain amount of force. But the catch is it's blocking it by filtering it. So again, we have this argument where the red's going to be coming out of here and the black's going to be coming out of here. So this is filtering. So not only does it first, the rule is the mass absorbs some energy. So this side has mass. There's mass between this point and this point that's much greater than the mass above this magnet, of course, and just this magnet by itself. So this mass below it is much greater. So there's less force coming up this way and more force coming down this way. So that gives you the basics of gravity. But the catch is here is the force that's filtering it here, that's blocking it, is now blocking it with this magnet in a segregated way, which means that all of this force will leak out of the magnet, making it even more, essentially taking more force from that's going this way and disposing of it in terms of it being a pushing force. So it makes this push even less this way, which makes this force stronger, obviously. So this force never gets any stronger. It's just that the amount of force being either consumed by acceleration or being diverted, and that is released in another direction, is going to increase at this one point. Now it's not true here, it's true here. The opposite is true where the magnet is, in the sense that, I could go into that explanation, but there's no point. Point is that it's always, charge is the same thing as gravity. It's just gravity filtered, which means that it can be released in a new direction. So instead of absorbed as acceleration, it's merely disposed of. It's merely, disposed of. I mean, it's it can't affect something because it's taking something that was heading right for you and making it not heading right for you anymore. It's now moot to being a pressure on you. So if I can make the rays that are coming to get me, if I can make them go a different direction, they can't hit me. Therefore, they can't apply a force on me. Then the force on the other side will win. It's sort of that simple. Alright, what's the other point I wanted to get to? Yeah, so I don't know. So the problem of detecting mass or defining something's mass, I think there's some other point I wanted to do, but whatever. So anyway, so obviously you can see that mass is kind of variable. Even though the mass of the magnet doesn't change, it really does matter where there's another magnet. The other magnet will change the mass of the magnet, essentially. It'll make it appear like the magnet's much heavier than it is because I've changed the environment. So the environment kind of dictates your mass by creating a change in the force around you. And that's really what moves you. So the point really is if there's a proton somewhere and there's completely equal force on it, you could say it has a rest mass of 0. I mean, it has no mass in the sense that nothing's it's inert in terms of displaying what we would consider to be the symptoms of having mass. There's no way to detect its mass, let's put it that way. So we can only detect something's mass by creating a force that can move it. And the force is always the same little mass bits. So let's just establish that they're just ones. They're just an amount of force, and a quantizable amount. They're just one force mass. And that these protons and electrons constitute something more than one force mass. And they only move because you hit them with force to make them move, or you hit what's associated with them. Okay, they're pressurized. There's a low pressure here. This low pressure ties these two objects together. Now if I move this object by hitting it with force, I might be hitting it with black force. It's always, this bit will move along because it's going to have more force hitting it this way than this way, and it will move in the direction of the least amount of force. So its mass doesn't do anything. It's not acting. It's being acted on to move. And how fast it moves or how much force it has nothing to do with its mass. So you could say if you take an electron and you keep hitting it with ping pong balls, right? So you take your tennis ball and you keep hitting it with ping pong balls, and you hit it with zillions of them, like really fast, blah blah blah, supersonic kind of thing. The tennis ball will start to move in the direction that it's getting hit, but its mass isn't really, what it has inside of it isn't nearly as important as the stuff pushing it. So this is really the force that the tennis ball has. So when it hits something, we can say, oh, it has a huge mass, but it really didn't have a huge mass. I mean, it hit the earth or whatever it's coming towards really fast, but it only has the mass that the force gave it. It's this force still pushing it that has the mass. And if I stop this current, so if I kill this voltage, this whatever this is some sort of, what do they use? What's the term they use? They use a term for like 1,000 volts. What's the term they use for that? Well, anyway, so could be lots of volts. And so the mass is, you're not measuring mass when you measure impacts. You're measuring how much force pushed the thing. Alright, so the point I wanted to get to was, so conventional physics doesn't really answer these questions very well about how an atom is actually moved, one of their atoms with their little electrons spinning around and their protons in there. They don't really explain how that atom is moved by gravity. They just say some crazy thing like space disappears here and it falls into the hole of the disappearing space, which, I mean, that might be satisfactory to you, but to me that's not an explanation of how the atom moved. I mean, because frankly the atom would have to fall into the hole and the front would fall faster than the back, and creates lots of problems. Well, anyway, so what I would point out is that I think what we know from evidence, experimental evidence, is that electrons do have to be pushed. You have to maintain the voltage, and as soon as you stop hitting them with the force, okay, they stop. They don't move anymore. That's it. I'm done. Turn the voltage on, they move. Turn the voltage off, they stop. They don't carry momentum. They don't keep going a very far distance. Like I say, they might keep going a little bit. And I've explained in much previous videos that this has to do with the fact that, say if I move something, something's moving, the field is still hitting it from the sides all the time, doing transfers. And so any momentum an electron or proton gets, is going to be wiped out by these interactions about these left turn ideas. And so the force is going to keep doing transfers where it releases this energy and keeps this energy, or it goes in this way that keeps this energy and it releases this energy. So there's always this perpendicular exchange going on, and so any force, any momentum it collects, it loses very quickly to the environment. But anyway, the point that's just important here is the electrons only move if you maintain a voltage. If you stop the voltage, they stop. And I think the same rule holds for protons, but obviously you're moving them with something different than voltage because it has to be red force, not black force. But regardless, in both cases, I think you can only argue that in gravity, an electron can't, like if we drop ourselves out of an airplane, we don't just go 10 meters per second. Every second we gain whatever, 8 meters per second. We gain a percentage of 10 meters per second and keep adding that to our velocity. So our velocity keeps increasing. So we go from falling 22 miles an hour to falling 44 miles an hour to falling 66 miles an hour. After 5 seconds, we're going whatever, 120 miles an hour. But an electron can't do that. It can't collect extra force. It can't collect momentum. It can't maintain a velocity. So it has to be it can't have too big a mass weight, because it doesn't demonstrate any capacity to hold that. So it will just fall 10 meters per second. No matter how many seconds it's in the gravity, it'll never go any faster unless you put a voltage behind it. So in a sense, you could say 10 meters per second is a voltage. I don't know how many volts that would be, but it's a voltage. 0.5 volts or whatever. So gravity is essentially a voltage, because it will move an electron a certain distance at a certain speed. And it'll do the same thing for a proton, but a proton won't go any faster than 10 meters per second. It can't gain any more than the actual speed, the actual mass equivalent of force that the gravity is producing. And the mass equivalent is the 10 meters per second. So that's all it has, and it can't go any faster. Yet a whole atom just made of these things, can go much faster. It'll do what humans do. It'll go 10 meters a second, and then after the second seconds, 22 meters a second, and then 33 meters a second, and it'll keep gaining velocity as it falls. And that's something physics doesn't really deal with. That there is something fundamentally different about how the force is captured inside of atoms versus how it affects the individual bits. And so I've sort of discussed this in dealing with the drag problem, that I think this is why certain atoms have to have a minimal structure to be able to increase their velocity faster than the voltage is moving them. And that would involve some arrangement of let's see, how do I want to draw this? Yeah, I sort of want to use so let's make this a proton. Pretend I didn't make that black. And that the electrons would be at that key 90-degree angle from each other. So this 90 degrees is important in terms of the idea of perpendicular. And the idea would be is that force would come in and get trapped in this cycle, where it would bounce off this electron, then go back and bounce off this electron, and go back and bounce off this electron. And if we call this a momentum neutral exchange of direction, then all the force is essentially in this direction if you add another proton here. Because now there's no force connecting these two electrons, so they're almost attracted, because all the force this way comes out of this proton, all the force here goes out of this proton, and the red force does the same to the electron in the sense that any force here goes out. So there's a strong low pressure here, you have a strong high pressure here as it collects more and more force, and the net result is the velocity will be in this direction of the whole thing. So as these electrons move forward, everything has to move with it because of the pressure differentials. Oh, this isn't, I'm sorry, that was deceptive. The relationship between the proton and the electron is low. The overall, this pressure between these two electrons is high. Alright. So, yeah, so gravity, mass is a really interesting subject. Some nuance to it, but again, all you have to do is these simple rules. I mean, it's only these simple, I don't even know if it's 4 rules, it just might be 2 rules. I mean, it's really not that complicated. Electron, proton. You have a black force, you have a red force. Plus or minus, however you want to do it. The black force, the red force leaks out of the black. The black force leaks out of the red. That is, its direction changes, which means it can't be trapped. And that's it. That function allows the universe to have a lot of complex relationships in terms of you just create some some arrangements, some geometric arrangements, and you have all kinds of complex force dynamics by just that simple rule. Alright, enough of a video, I think. Not a great day. I have not great days now and then. So yeah, is that enough? Oh yeah, you know, I could go on. You know, the Professor Lewin thing. He did something. You know, April Fools joking. I mean, you know, I really hate, you know, 90-year-old children. But anyway, it's I wish they just. It's another test. You know, it's another moron signaling. You know, if you have pubic hair and you still give a fuck about goddamn fucking April Fool's Day, yeah, you're just moron signaling. Kill you. They should just shoot you. That's all. They should just shoot you. So anyway, but his answer, I watched his half-hour answer. There's probably no point in me doing a video on it because no one, I think, else is going to pay any attention. From 20 years ago. And the second half of it didn't make any sense at all, frankly. It's conservation if you choose a point over here, but it's not conservational if it's... No, it has to always be conservational. Why are you saying that? It has to always be conservational. You always have to get the same answer, no matter where you put your stupid point. You have to get the same answer. That's the rule. The math can't have different answers. So why are you implying it comes up with a different answer? It has to be the same answer. I just didn't get it. But anyway. So apparently, look, I'll do a real quick one, just so I don't have to do a whole video. The idea is you're pushing a ball. Alright, now I said, look, just make it something in space because it makes it so much easier. Because it's this whole idea of skid. You know, you hit something with a force, it skids a certain amount, and then it starts rotating by a certain amount. And where do you hit it to get, you know, skid versus rotation? And how do you know how much skid there is to how much rotation depending on where you hit it? Okay, and the thing is that there's apparently this 2/5 rule. Okay, so when you get to this 2/5 line, apparently if you hit anywhere above that, it's all rotation. Now I didn't say it exactly that way. He said there's some other kind of crap that I don't quite understand. Maybe it skids in backwards or something, but I don't know. So I don't know where the 2/5 rule came from, because frankly it doesn't seem to me on a spaceship, if I had the little jet here that shot out force, that I'd still end up moving my center some portion and I'd spin some portion, but that I wouldn't be all spin, and it wouldn't be all spin till I was truly on this edge or further out. So if I could put the rocket here, then I'd clearly cause all spin, but I don't, frankly, I don't know where that rule comes from. I don't know how it's proven. But the other point I would make is that you can illustrate it as being something moving in the sense that the amount of distance it moves by skid is the same ratio as the distance of rolling. So you just measure this line. The length of this line will equal this line. So this speed will be a little bit slower than the rotation speed, will be a little slower than the skid speed to equal out to the same movement of the center of mass. They both cause the same amount of movement of the center of gravity, but the rotational speed will be slower in meters per second because the rotation will cause, if it's the same speed, cause the center to move too fast. Something like that. Anyway, enough. There's lots of ways to get answers, you know, and that's another thing is, you know, there's not one formula or one method of mathematical analysis that provides answers. There's always different ways to approach the problem, and it's just not enough. It's not enough concession to that truth in much of how physics is taught. They teach it one way, and that's it. They don't even pay much attention to the fact that you can get the same, derive the same answer through a different method. But anyway, enough of that. So, till next time and such.